let's resume this class. This is the third class, and we closed the last class with the brief introduction of Hodgkin-Huxley formalism. So, I am not getting into the mathematical derivation of it, because that is beyond the purview of this class. There is these two classic, or I think 4 classic papers which were published in Journal of Physiology back in 1940s and 50s. Thick paper, each paper I think 35 pages of papers, were based on this data. They developed the model, mathematical model of it, and that is what famous we know as Hodgkin-Huxley formalism, explaining the events which possibly could shine light on the whole event of action potentials which are being generated by an excitable cell. So, there are 3 events, once again repeating to you. There is a flux of sodium ion, they are very sure about it. How they are entering, they were not sure. They said that there are pores which are unidirectional, and then they say there is an efflux of the potassium ions, making it far more positive, as you could see, far more positive out there. And then the balance is being restored by some means, they said, either pump out or something, where sodium is being thrown out of the cell and potassium is being pulled back. Today's knowledge says this sodium enters through a very specific route. If this is, so now we are trying to explain this in the light of the modern day, where the cell looks more like this. You can make it spherical or whichever you want to make it, and you have the lipid bilayer, and you have there are these channels. So, sodium enters through a specific channel or called sodium channel, and during 1940s or 50s there was no concept of channels, and these are called ion channels. These sodium channels are 2 kinds, and they open only in one direction. They are like this structure of electronics. We call them diodes. They carry current only in one direction, not in both directions, right. So, just like them, you have these sodium channels which carries the sodium inside the cell, and their opening and closing is dictated by either voltage across the membrane or a ligand binding. Both of them are important for biosensor research. We will come to this. When we talk about the voltage part, that means if outside it is positive versus inside it is negative. Now, if you vary the voltage by some artificial means across it, then these channels will be opening. That means voltage gated, means the gate will of the channel which will allow the sodium to pass will open when there is a certain voltage across the membrane, and this kind of channels are called voltage gated ion channel. Voltage gated ion channels. But when Hodgkin and Huxley were making those formalism, even the very understanding of the membrane structure was not clear. Nobody knew what membrane is. There are all sorts of theories in the market. Nobody knew. Microscopy was nowhere there of the level of electron microscopy or scanning electron or transmission electron. Microscopy was at its infancy. right? There was no crystallography. The first crystal structure which came was hemoglobin by Perutz, that is 60s, right? Nothing much was known, and yet they could give a hint. There may be certain kind of pores or passage through which it passes, and that's why that formalism was given the due honor in the form of Nobel Prize. Hodgkin and Huxley got the Nobel Prize for their work. There were other people at the time who also shared the Nobel Prize with them, and they also worked in that area, but I'm primarily talking about the key work who contributed. Now, these voltage gated channels, or similarly these ion channels, could be also ligand gated. When you talk about ligand gated, means ion channels. When you talk about ligand gated, means there is something which binds to them and open their gate. And another interesting part of this pore through which the sodium passes is very specific to sodium. So, it is a selectivity pore. So, first it has a direction, it is selective, and its opening and closing is regulated on the basis of voltage. So, it seems if we draw this protein, it has a, and this is a protein structure, it is a very complex protein structure. So, it seems this protein has a voltage sensor. So, it means there are amino acid sequences which could sense the voltage. Sensing voltage. It has a pore region which opens, it has a selectivity pore region. Selective pore region, and it has a gate region. So, these are the evolutionarily most magical things, probably the most magical sodium filter ever formed, and these are simple proteins which are embedded on the membrane, and they do all these magical things on the surface. You understand? These pores are like wow. Put a voltage across them, they sense the voltage, they open up, but they can only do that when they are embedded in the membrane, right. So, the first event what happens here is there is a movement, unidirectional movement of sodium inside. Second thing what happens is there is another set of channels which are called potassium channels, and 1999's Nobel Prize went to Roderick MacKinnon from Rockefeller. He is one of the pioneers who figured out one of the structure of one of the potassium pores. Initially, it was believed to be a channel, but later it was discovered it is a pore, but the credit goes to him. Sodium channel structure is still not clear. Okay, so still no one has won a Nobel Prize for that structure, but the potassium. Now, the potassium structure is again that it allows to potassium ions to flow outside only, from inside to outside, and this too acts at a certain voltage range. So, it seems our excitable cells have lot of voltage sensors. They could sense different, almost they are like a voltmeter, as if there is a amino acid sequence, they could sense one certain kind of voltage. There is another amino acid sequence, they could sense another kind of voltage. They are all electrical elements of nature. They all could sense all these different kind of voltages. Now, these ones allows the potassium to go out. These are called voltage gated potassium channels, or sometimes they are also called delayed rectifier channels. Interestingly, Now, I bring you back to that action potential image. If the sodium channels are opening in this range, in this voltage range, somewhere in this voltage range, they fully open. Look at the voltage, then the potassium channels will open only in this range. So, that is the specificity of it. So, this is the range where lot of sodium influx, or this part is happening, but there is a lot of sodium is entering the cell, right, followed by again another set of cations which are leaving the cell, making the inside the cell extremely positive, but the directionality is like this. But the critical part for you to understand, they are gating or they are opening or their gate open at very different kind of voltages. So, these ones, well, these are opening at this zone. So, if this is minus 90, these are opening at around below minus 50 millivolt, and they will shut down by the time you reach somewhere here. So, their active range is somewhere here, minus 30 or minus 40 to minus, say, 10. After that, they shut down. See the beauty of it. A gate opens, gate closes within a narrow window of voltage, say minus 30 or minus 40 to minus 10 or 10. That's it. Followed by, as it is increasing, there is another set of voltage gated channels open, which opens from inside to outside, only allow the cations. There are two cations we are talking about. We are talking about sodium and we are talking about potassium. The second cation, which is potassium, it goes from inside to outside, making the cell even kind of, balancing it out a little bit. Now, this is an interesting phenomenon. Followed by, so if this one works here, so this is where it is kind of, pulling it back. Followed by event which even Hodgkin-Huxley did not know. Even they were not even aware of all these potassium channels, sodium channels, nothing. They say there are potassium pores, there are sodium pores possibly. Is the word of third thing, which I will show it like that. Those are pumps. In this case, these are sodium, potassium, ATPase pumps. What are these pumps? These pumps binds to bunch of sodium from inside the cell and binds to a bunch of potassium inside the cell at a certain stoichiometry, and they revolve back like this. So, this pump, so it binds to sodium here and potassium here, it just twists back using the ATP, that is called ATPase, and restore the balance. What I was drawing here, go back, yeah, exactly here, restoring the balance. This is the third one. So, this is where the pump is acting. This pump is binding to the sodium on the inside and twisted back and brings the potassium inside and restore the harmony back to the normal situation. So, you see there are three molecular events: voltage gated sodium channels opening and allowing sodium to get inside the cells, voltage gated potassium channel leaving the cell so that it does not become extremely positive. So, bringing it down, net positive charge is going out. Then in order to restore the homeostasis, there is a balancing act which is happening where we are getting the sodium potassium ATPase pump to restore the balance. These are three critical events which led the foundation stone for next 100 years of electrophysiology, understanding the biosensors, understanding the structures, understanding the molecular architecture, and tremendous amount of work is happening across the world, and organizations like NIH, EMBL, all those giants are spending trillions, zillions of dollars in order to explore the structure of these molecular machines. These are the machines which does some phenomenal thing in our body. Okay. So, summarizing it through, so you have the voltage gated channels, ligand gated channels, voltage gated sodium channels. To summarize it, we have activation of voltage gated sodium channel, then voltage gated, or they also called as, and figure it out why they are called delayed rectifier channels, potassium channels, followed by sodium potassium ATPase pump. These are the critical players of action potential. Now, that brings us to a very interesting thing. If all these things are voltage gated, now think of a situation. So, there is one more concept before I get into this. Is what I wanted to mention is, I told you that these voltage gated sodium channels has a narrow voltage window in which they work, and they start to get activated at around minus 30 millivolt, and they will remain active around up to say 0 millivolt. You just have to cross check exactly up to what is the window of it. And most of these potassium channels are opening at plus 10 millivolt or something like that, right? Now, if a cell reaches something like this, then there is a cascading event of all the sodium channels will open like a domino effect, and that is the zone where action potentials are called all or none. That means, if you could take the membrane voltage by some means to minus 30 or minus 40, then you will see a domino effect of all the sodium channels opening through. And this will almost is the zone where the cell goes for a blackout. Boom, it crosses the 0 millivolt mark and shoots positive. That's why action potentials are called all or none phenomena. Either it will happen or it will not happen. If it happens, everything will move like this. So, that brings us to a very interesting point. Before I explain something, I wanted to tell you that why I was kind of waiting to reach to this point before I could explain these cells, which are spontaneously active. So, that means, in a system, the cells which are sitting in this zone, there is a possibility that such cells will behave in a spontaneous manner, and that is why these kind of cells which are spontaneously active, these are called pacemaker. They pace up the circuit, and such pacemaker cells are another miracle of nature. They do not follow the kind of action potentials what you see here. They follow a very different kind of action potential pattern. And before I move further, I will explain another set of action potentials before I really get into the how the voltage gating channels could be exploited, how these cells could be exploited for biosensors development. I will talk a little bit more about couple of other things, which includes your, get to the slide, about action potential of the next excitable cells called the cardiac myocytes and of course followed by the pacemaker cells. And these two will be important before I move on to how voltage gating could be exploited. And we will talk about all these things in the backdrop of the development which are happening in the field of bioelectronics and biosensors. Okay. So, I will close in here, and in the next class we will talk about the action potential of cardiomyocytes. In the next class, and we will talk about it. Thank you.